Hello everyone, in this video we talk about gradient descent. Gradient descent is a simple yet powerful method used in machine learning to help models improve over time. It works by making small adjustments to the model's predictions, gradually getting closer to the best possible outcome. Think of it like finding the quickest way down a hill. You can take small steps in the direction that leads downward, and this process is important because it helps models learn from data and make better predictions. To review what we had in the previous lecture, recall that in a linear regression problem, we are given a data set that contains input and output pairs. So these inputs xn in general are d-dimensional vectors, and these are the inputs to the machine learning system. And the outputs are, in this case, continuous real-valued numbers. And that's why we represent them by yn that belongs to the real-valued numbers. And the input is a d-dimensional vector. We discussed this in details about how we can write the loss function for linear regression in a compact form using vectors and matrices. To recall how this works, remember the idea behind linear regression is very simple. We have these inputs xn, this lowercase n represents the index for the sample, and then we have the unknown weight vector or parameter vector w, and the output, and what is actually used to approximate these yns is simply the dot product or inner product between w and xn. So they both should be vectors of the same length so that we can find this dot product or inner product. And because of this very simplified assumption that we make here, now we can put everything in the form of vectors and matrices, meaning that we have a vector for the outputs that we show using y. This is an n-dimensional vector because it contains y1, y2 to yn. So we put all these outputs in this vector. For the inputs, the story is a little bit different, and that's because each input by itself is a d-dimensional vector, and now we have to stack these together. So in general, we have this option to stack them vertically or horizontally. The approach that we take in this course is to stack them in this form of vertically. So we have x1 transpose, so you can think of this as 1 by d plus 1 vector, so it's a row vector. And then we have x2 transpose up to xn transpose. So now in this case, we have n rows, and each row corresponds to a data point, and we have d plus 1 features, and each column corresponds to one feature. And if you're wondering why we have d plus 1 here, that's because in order to be able to have this compact form and include the intercept term, we assume that the first feature for each observation or each input is 1. So technically, the first column of this data matrix X is all ones. And in this case, we have the original features plus one extra feature for that extra one that we have. And similarly, we can have a vector W, which contains W0, W1 to WD, which means that we have D plus 1 elements or variables here. And this is what we really want to learn. Something that I want to focus here and emphasize is that y and x are provided by this data set that we have. So this data set includes already all the values of inputs and outputs that we have. And for this reason, y and x here are fixed or given to us. What we're really trying to optimize here is to find the best possible weight vector or parameter vector w such that these predictions are as close as possible to these true outputs. And in terms of the compact notation or formulation that we have here, this means that if we multiply this matrix X and this vector W, this corresponds to dot products or inner products between this vector W and each data point that we have. So therefore, these are all the predicted values. And we want these to be as close as possible to this vector Y. And for this reason, we are using the L2 norm of vectors, which is y minus xw. We have the L2 norm square. This is also the sum of the square of the differences between true and predicted values. That's what we showed previously. And for this loss function, which is known as residual sum of squares, we also use 1 over 2. So we saw this last time. The reason that we use this 1 over 2 is that otherwise we have to deal with an extra 2 when we find the gradient of this loss function with respect to w. So having this 1 over 2 in the original formulation, it does help us to get rid of the 2 when we are finding the gradient. But as we know, derivatives or gradients are linear operators. So in general, it does not really matter what constant we have here, because we can do a simple math and find the appropriate constant that we have to use in the gradient formula. And you can see that in this case, the simplified case that we have for the gradient is x transpose times xw minus y. And here you can see that the dimensions do match. So y and x times w, they're both n-dimensional vectors. If we remember, x is n by d plus 1, so x transpose is d plus 1 times n. And if we do this multiplication, we get a d plus 1 vector. And that's what we want, because remember, when you find the gradient of a function with respect to, let's say, w, and w has 5 elements, the gradient should also have 5 elements, because each element of the gradient means the partial derivative with respect to that element of w. So therefore, this is important to make sure that the gradient of this loss function has the same number of elements as what we are taking the gradient with respect to, which is this w. There's also another way here to make sure that this formula that we have, that we derived before, is correct. And that's, remember, if x times w is exactly equal to y, this means that we have found the correct or the optimal solution w. And in that case, you want to make sure that the gradient or the derivative is 0, because you're at your optimal solution. And this is the case. So if x times w for a given w is equal to y, then the gradient is 0, which means that we found the optimal solution, and that's what we want. If the gradient is not 0, that's problematic, because this means that we can further reduce the value of the loss function, and that means that the solution that right now we have is not the optimal one. So that's why this is very important to have this property that if x times w is equal to y, the entire gradient should be equal to 0. So based on this review that we have, and here we have the general flowchart or diagram that we have for training machine learning models. As you can see, this is how we do the transformation by finding the dot product or inner product, and then measuring the differences between true and expected values using the loss function or cost function. So last time what we did to solve the linear regression problem was, well, we can set the gradient equal to 0, and you can see that x transpose x, w equals x transpose y. And since we want to solve for w, you can find the inverse of x transpose x, and this should give us the solution. And although, because this is a very simple problem, we can find the solution in a closed form, or we can find the solution analytically, there are several algorithmic issues. The first one is that we have to find the inverse of this matrix x transpose x. And that can lead to some numerical issues if x transpose x is ill-conditioned or has singular values that are very close to 0. So in that case, when you want to invert those singular values, that can cause numerical stability problems. And then the other problem that we have here is that beyond numerical reasons, that finding the inverse of a matrix is difficult. And in general, if we have a square matrix of size d by d, where remember d is the number of dimensions, finding the inverse, the time complexity is the order of d cube, which means that if we double the number of features, then the cost is 2 raised to the power of 3, which is 8 times more. So you can see that in these cases, we say that the problem scales very poorly, because it's going to take a very, very long time to solve this linear regression problem for a very large scale problems. Let's say you have some like gene expression data where the number of dimensions is usually in the order of like tens of thousands. then that can take a very long time to find this inverse. And then the other issue that we have here is that if you have a huge matrix X, so let's say you want to solve a regression problem where you have millions or billions of data points, and in that case, the issue is that you may not even be able to find this X transpose X because it's hard to store this X in the main memory of your computer, right? So usually you have 16 gigabytes, 32 gigabytes. So if this X is huge, in a very large scale problem, that can also be another problem where you cannot really solve this problem directly. And that's why we want to talk about gradient descent. As we said, gradient descent is very popular in machine learning and deep learning. And you can think of it as a generic optimization algorithm. So anytime that you can find the gradient of a loss function, then means that you can use this gradient information to tweak the parameters that you have in an iterative fashion to minimize this loss function. The trade-off here is that you may not find the best optimal solution, meaning that the absolute minimizer of your loss function, but it is very likely that you can find a really good solution. And for many machine learning and deep learning problems, that's still very impressive if you're able to find a relatively good solution that can lead to accurate predictions. And most importantly, when you're doing gradient descent, you really don't need to anymore use matrix inversion. And that's something very helpful. So in order to start with the idea of gradient descent, think about it this way, that you have a scalar function, f of x. So this means that in this case, the function accepts a scalar x, a real valued number x. And then we apply this function. And in this case, f is just a generic or a general function. You don't need to think about this right now as a loss function. And in order to be able to find the minimum value of this function, and in particular the minimizer, because in many cases in machine learning, the minimum value does not matter as much. We really want to find what, for example, in the context that we have, what value of w minimizes this loss function that we have. So with that in mind, what we really look for here is the minimizer of this function. And in order to find this, we can start with a random guess. And in that case, we can tweak that to make it a better guess. And in order to do this, we assume that right now at iteration k, this is the solution or the minimizer that we have, which is x index k. So this k here is the index that shows the iteration number. And then we find the gradient of this function. Here, since I have a scalar function, I can really use like derivative, but I'm using gradient just to be consistent later on, because in this course, we mainly talk about gradients because we have more than one variable. And in this case, we can find this gradient of this function at this point xk. And if the gradient is positive, this means that if we go to the right, we are going to increase the value of this function. And in order to decrease the value of this function f of x, we need to go to the left. And that's exactly why we have a negative sign here. So in order, again, to explain this, we have a current solution. We are going to subtract the gradient. And in general, you may also want to have more control on this to see how big each step is going to be. And that's why we also have this eta, which is the learning rate, or also known as sometimes like a step size. And overall, we get this update formula where we have the current solution minus eta learning rate times the gradient, and this is the new solution. So I want to make this clear that this equality here is more like assignments that we are using in programming. So this means that we're going to find the right-hand side and assign this to what we have on the left-hand side. So just to make sure that this makes sense, so let's look at a very simple case. Let's say you have a function f of x, which is just x squared. In this case, if we want to find the gradient, or again, just the derivative of this function, since we only have one input, it's 2 times x. And let's just implement this update formula that we have. So what we really need here, we need an initial solution. And in this case, we assume that the initial solution is 10 or any number that you want. And also, I create a Python list called results, which includes this initial solution and the future solutions that we're going to find. So the idea here is that I'm going to create a list with only one element, and then I'm going to add more elements to this list. And that's what this .append method is. So this .append method is going to add what we calculate in the future to this list. And really, in order to implement this update formula, you need to use a for loop in the simplest case, right? So you use a for loop for I in range 10. So it means that we want to repeat this process in the for loop 10 times. And what you do is that you find the value of the gradient or derivative at that current solution. You multiply that by eta, and here right now eta is an input parameter that we have to provide. So in here eta is one of the inputs to this function, and once you get that value, you apply that to the gradient. And what we have here is actually equivalent to saying that we want to multiply eta by the calculated value of the gradient and then subtract that from x. So this notation that you can see here is the simplified or more compact way of representing the same thing that we have here. So I'm going to just delete this for now, but I wanted to make sure that it is clear what this negative equal sign means. And once you update this x, because this is an assignment, you're going to create a floating point. So just in case if x is not a floating point number, we want to enforce that here. And then we're going to append that to the results list that we have. And when we are done with these 10 iterations, we're going to return the results that we have. So let's run this cell. Right now, we have not done anything. It's just this is defining functions. Also, we have another function here that we need because we want to visualize how this gradient descent works to make this easier to understand. So what we do here is that once we have obtained these results list that we want to create a plot that shows the progress of these values of x or results that we have. And in order to do this, we assume that we are given results in this case. We find the minimum and maximum value. We find the absolute value to make sure that that's positive. And then we create a list of numbers from negative n to n. So this is kind of optional here, but I want to make sure that the plot that we have is somewhat symmetric. So that's why I really want to know what the maximum value that I need to have. And then I'll go from negative that value to positive that value. And here the step size that we use here is this 0.01. So this is, again, optional. You can use 0.1. Obviously, you want to use most likely something less than 1, but it doesn't really matter as much because it's very fast and efficient to work with NumPy arrays. The other thing that we want to do here is that first we want to plot the function f that we have here. So here f of x is x squared, but regardless of what exactly f of x is, because we can just change the definition of f of x, we create these x values that they're from negative n to n, and that's how we find n. And then for each value inside this f underscore line, we're going to compute the value of the function. And in this case, we use plt.plot to visualize this plot. So these are all the x values, and this is how we find all the y values. So x versus y. And then the other thing that we want to do is that when we find these solutions that we have stored in results, we want to connect all the neighboring data points. And in order to do this, we are going to assume that now we have the first two values in the list results. We find the y values for this, and then we are going to connect them using this blue line. So this B is here stands for blue. And this O is the marker that we are going to use. And similarly, we're going to add a very small information in the form of a text message next to each data point here, each member of these results, to say that the iteration number that we have. So if the first iteration is 0, then the next one is 1, the next one is 2, and so on. And here, the way that this plt.text works is that we have the x and y coordinates, and then the text that we want to show. And there are some also like optional arguments like font size, horizontal alignment, vertical alignment, and so on. So in this case, we usually don't talk about all these customizations here, and you're more than welcome to change them. But usually the main ones are the first few ones when we have any function. And also, in order to make this function look, when we plot it to look nicer, we can add the x label, y label, and also plt.show to make sure that we actually visualize the plot. And something else that we can do to make more exciting figures is to adjust the font size, the figure size. So all of these are optional and you can adjust as you wish. So now what we do is we're going to use the show underscore trace function. And we have to pass these results, right? And results has its own function, right? It's called this GD. So we have to first call GD, provide the learning rate or the step size, which is eta, and this f underscore grad. So we don't have to be worried about this f underscore grad. It's already given, but we have to provide this eta. And this is important because I want to show you the impact of the learning rate here. So here the learning rate that we use is 0.15, and also we provide f grad. So if I run this cell, then we should be able to see the plot that we just discussed about. And so here you can see that this red curve is the function x squared, right? So at 10 is equals 100, and we want to find the minimum value of this. So in this case, we know that the minimum value is 0, and actually the minimizer is also 0. So for 0, this function achieves its minimum value. But because we're using gradient descent, we're going to start with a random guess. And if you look at it, a random guess is actually at 10, right? So we start from here. And for 10, the value of this function is 100. So you can see that we have here 0. So this means that this is iteration 0, our initial guess. At this point, we are going to look at the gradient. And since the gradient is positive, we have to go to the negative side. So that's where that negative sign in the update formula comes to play. And now from this point, we find the next solution, which is shown by this number 1. So that's the solution we have in iteration 1. And you can already see the value of this function at this point is definitely smaller than the original value of that function at 10, which was 100. And then we do another round of update, and we get to this point, and then 3, 4, and it gets a little bit hard here, but you can see that we slowly get closer and closer to the optimal solution or minimizer, which is 0. So in this case, you can see that this works very well. But just to show you the impact of the learning rate, it does very much depend on what this learning rate is. Meaning that if it is too small, let's say we make this really small and run this cell again, you can see that we start at 10, but we are making very small progress. So I see we're very far from the optimal solution. And in this case, if you really want to use this learning rate, you have to increase the number of iterations, right? So maybe instead of 10, you can use 100, 1000, or something like that. And on the other hand, if you choose something that is too large, like let's say 0.95, you can see that doesn't look great either, right? Because we start from here. And then since the step size is really, really large, we're going to actually more like, oscillate around the optimal solution. So we're going to go to the other side. And then we go to the other side. And then this, happens a lot. And it is very likely that we never will get close to this minimizer or optimal solution because of the fact that we are taking huge steps. So therefore, gradient descent is a very fantastic optimization method, but you need to keep in mind that the learning rate or step size is extremely important to be tuned. So let's go back to the original value that you had was 0.15, and you can see that this is gives us a good solution, even with 10 iterations. Okay, so now let's talk about gradient descent in general. By in general here, I mean that when we have optimization variables like W here, that they are not a scalar anymore. They can have, a few tens, a few hundreds, or even more unknown variables. And so in this case, what's happening is that, so we want to find the minimizer of this function. So we assume that at each iteration k, we have this solution, which I call it an old solution. And then we're going to subtract this by eta times the gradient calculated at that old solution. And this will give us the new solution. And what this means is that if, let's say, we want to apply this to the linear regression problem that we have, and just to make this a little bit more interesting, instead of residual sum of the squares, we are working with mean squared error, which is MSE. And the only difference is really this, scaling that we use here. So since this is like a mean or average, so we have to use 1 over the number of data points, which is the uppercase N. And then we have the L2 norm square of y minus xw. The nice thing is that you can actually write this in terms of the residual sum of the squares. So if we have a 2 over n, and then multiply this by 1 over 2 y minus xw normal squared. So this is exactly residual sum of the squares and shows the relationship between the two loss functions. So again, the goal here is to show you that, we usually don't have only like one type or one kind of loss function. So you can have different loss functions with different scaling factors or even different terms that we can add, as we're going to see later on in this video when we talk about regularization. So you can see that the mean squared error is 2 over n times residual sum of the squares, which means that if we now take the derivative or gradient of both sides, now we have 2 over n gradient of residual sum of the squares, and that's something that we already calculated. It's x transpose xw minus y. So if you want to apply gradient descent updates for linear regression, it's very straightforward. We already know the solution for iteration k, so that's our best guess at iteration k. And then we're going to subtract eta times this gradient calculated at wk, right? So this works for any w, including wk. And this will give us the new solution wk plus 1. And the nice thing here is that in this case, we do not need to find any matrix inverses. So you can see that in this case, it's just a simple transpose times another vector. So there's no matrix inversion involved. So that's one of the things that we wanted to accomplish, and you can see that gradient descent can do this successfully. So this is what we just discussed in the lecture note that we have. So now let's just implement this. So in this case, we're going to use a simulated data set, because the goal is not necessarily to solve a regression problem on a real world case. It's just to show you how the gradient descent works. And then later on, through exercises and other approaches, we're going to work on real world problems. So in this case, we assume that we have 100 data points. Now we have to create both the inputs and outputs for our data set. For the inputs, we assume that they are uniformly distributed from 0 to 2. So this function np.random.rand creates uniformly distributed values from 0 to 1, but we are multiplying this by 2. So now it's going to be from 0 to 2. And we assume that the way that this output relates to the input comes from this 4 plus 3 times x. And to make this more interesting, we are adding some Gaussian or normal noise. That's why here we have rand n. The n here stands for normal distribution. If we don't add any noise, then the problem is trivial, because we can just pick 2 data points and find the line that goes through them. So therefore, we really need to add some noise to make sure that this problem is not trivial to solve. And then we can just plot this to show how this data looks like, right? So it looks very much like that life satisfaction data set that we had before. except that here we have a simulated or synthetic data set. And remember from the previous slide, the way you can solve this is to have a column of all ones. So that's that extra feature that we can include if you want to solve this problem manually or we want to solve this from scratch. Obviously, scikit-learn will take care of this, but in this case, I want to find the best solution by setting the gradient equal to 0. So that's why I'm going to add that column of all ones. And this np.c means that we want to concatenate these to column-wise, because the first column should be all ones. And in order to find the solution, we have to multiply x transpose by x, and then find the inverse of that, and then multiply that by x transpose y. Something also I do here, I'm using this @ sign for multiplication, which is allowed in NumPy. It's not something that I recommend you to use a lot because it sometimes can get confusing what this means. But if you're wondering, in this case, @ sign means simply matrix multiplication. And you can use just np.dot. That's something that overall can be less confusing. And in this case, again, since this is a small problem, we create this matrix x underscore b, which is a concatenated matrix with the column of all ones. We can set the gradient equal to 0, and we can find the best solution, which is 4.21 and 2.77. Which makes sense, right? Because we know that the answer should be close to 4 and 3. So overall, we are not able to exactly recover those values, but that's okay, because we added also this noise term here, right? So you can see that when you add more noise, you get solutions that are farther and farther from this optimal value. So that's something that, always to keep in mind when working with real world problems. So now let's see how the gradient descent works if you want to solve this problem using gradient descent instead of finding the matrix inversion that we had to do before, right? Because before we had to use linalg, which is the linear algebra implementation in NumPy, and we had to use this matrix inverse. So in this case, we have to, instead of finding the matrix inversion, define the learning rate, which I put that to 0.1, number of iterations or number of steps, which is 100 here. We need to start with a random solution. We're going to use a random vector filled with normally distributed values of size 2 by 1, because we have two unknowns here, so it should be size of 2 by 1. We also print the initial solution to just show you what this initial solution is, but the main part of gradient descent is just this for loop with 2 lines, and we can even write it in 1 line. So you can see that this is pretty straightforward. You need to find the gradient at the current solution, which is W, and then you're going to update W with this formula that we have on the right-hand side. And that's why gradient descent is very important in modern machine learning and deep learning, because it's very simple to use. There are some obviously caveats, such as being very sensitive to the learning rate and so on, but overall it's very easy to implement. And you can see that we start with this initial solution, and we get solutions that are close to 4 and 3, and that's what we expected to get. And one thing that is nice here, I can run this cell multiple times. You can see that the initial solutions are different, but usually the final solution that we get, the first one is close to 4, the second one is close to 3. So you can see that we can run this multiple times, and you can see that we start from different solutions, but eventually we get very close to the optimal solution at the end. In the next cell, what we're going to do is to investigate the influence of learning rate. And in particular, I want to consider 3 different values of learning rate for this specific problem and see what will change in terms of the final solution that we get. Since we are here working with a linear regression problem, when you want to plot the prediction model that you have, you only need 2 points on that line. So here we only need, let's say, 0 and 2, the beginning and end point. And if we connect them, that's the line that we have as the linear regression model. But do not forget that you have to concatenate that with a column of all ones. And in this case, we need to have 2 rows and 1 column. So because we only have 2 data points. And now let's say that we want to do gradient descent, but we also want to plot the lines that we find, the predictions that we find as we progress. So this for iteration in range n iterations, that's the for loop that we have for gradient descent. And you can see that this part that I'm highlighting, that's exactly gradient descent. You find the value of gradients at the current solution or old solution, and then you find the future solution or the new solution. But the only thing that we added here is these couple of lines here. And we want to plot these lines that we find based on the solution that we find for W, because each value of W corresponds to 1 line. And we want to plot these for the first 10 iterations. So what we're doing here, we are saying that if iteration is greater than 0, then plot these lines using a blue line. But for the very first iteration, use the red line. So the first solution corresponds to the red line because that corresponds to the values of what we have in W for the initial solution. And then we have other lines that we find as we update W. So that's the only thing that we add here to our gradient descent to make sure that we can visualize the result. So we can always look at these values of W, but they do not probably make much sense. It's much easier if we can actually show what that W corresponds to or translates to if we actually have this line in a 2-dimensional space. So here we just define the function. And then what we do is that we're going to do find our initial solution, which here again is a vector filled with normally distributed numbers. Something that we're going to also do here is that in terms of reproducibility, we're going to add this seed number here. And what this means is that after this, when we are creating this vector W, it's a random vector, but every time that you run this cell, you should be able to see the same random vector. So this is important when you want to make sure that your code is reproducible. And therefore, in this case, we specifically set the seed number to a number. So it shouldn't be necessarily 42. It's a very common number when you look at the documentation page for NumPy or scikit-learn. But in general, it is a good idea to make sure that we can reproduce our results. And if not, like before, when we ran this cell multiple times, you saw that we got different values of initial solution. So in that case, we just want to avoid that problem to make sure that we always start from the same place and now look at the impact of different learning rates. Something is small, something kind of like in the middle, and something that is large. And if you run this, and we're using also plt.subplot, so this is going to be a 1/3 plot. So you can see that's why it's 131, 132, and 133. So the last one shows the index or the location where we have 3 of those locations. And you can see that here, when the learning rate is too small, right? So we always start from this red dotted line. That's our initial solution, which we assume that it's red. And then you can see when it's small, it seems that we're getting closer and closer in terms of our prediction model, but we are not yet even close to where our data is actually distributed. When we increase it a little bit, you can see that it definitely is getting better, right? We start from here and then we quickly move and get closer to where these data points are. But you can see the issue. So this is like one of the, really like a big problems. If your learning rate is too large, you can see that instead of getting closer, we are actually like diverging, right? So you can see that there is one small little piece of a blue line here. So it means that at some point we were below this red line, and now we are all the way on the other side of where these data points are distributed. So this is very much similar to what you saw when we had this function when we use the value of learning rate, I believe, to be like 0.95, because then we were oscillating around the optimal solution. And this is exactly the same type of behavior here that you can see that by performing more iterations, you probably end up either on the right side or left side of these data points. and then we never get close to the optimal solution. So in this very specific case, the value of eta is very important. So far we discussed this application of gradient descent for solving linear regression. And the nice thing was that we could avoid the part that we have to find the inverse of this x transpose x. So here there's no matrix inversion that you have to be worried about. But there's also one more issue that we have here, and the fact that we have to work with the entire data matrix X. And if you remember, we mentioned that earlier on, that in many cases, the data set that you have might be too large, such that you cannot even store this entire data matrix in your main memory. And this is the idea behind stochastic gradient descent. So a stochastic gradient descent, in the simplest form, assume that instead of working with the entire data set, you want to work with one data point or one sample at a time. To explain this, remember, if you want to work with the mean squared error and minimize that, here is the gradient of mean squared error. It's 2 over n x transpose xw minus y. But let's say right now you want to reduce this matrix to only one row, because remember, each row corresponds to one data point. And I show that row using xn, and I assume that xn is a row vector. So what this means, it has this dimension 1 by the number of elements we have in the column, which is d plus 1. So if we replace or substitute, it's better to say, substitute this reduce x into this gradient formula that we have 2 over the number of data points. And right now, effectively, we have only one data point because we are looking only at one column, or say one row. So that's 2 over 1. And then x transpose, so if this is x transpose is xn transpose, which is a column vector, right? So we have a row vector, we transpose that, so you have a column vector of size d plus 1 by 1. And then inside here, we have x times w, so x is a row vector now, w is a column vector, and then we only have to include the y value for that very specific row that we selected, which we show that using yn. So just to recap here what we have, so we get this constant here too, because now we only have one data point. X transpose is just xn transpose, just a column vector. And x times w is this dot product or inner product between xn and w. So obviously when we do this multiplication or this dot product, the result is 1 by 1, which is a scalar. And we assume that the output for each data point is also a scalar. So in that case, this would be just a number times this column vector. And this does make sense because remember, the gradient should have the same length as the number of unknowns that we have. And in this case, we have d plus 1 unknowns. And this is exactly what we need. We need a d plus 1 dimensional vector. So if we put everything back into the formula that we have for updating the w values using gradient descent, or here technically a stochastic gradient descent. So this means that at each iteration, you pick one data point, and I show that data point with this index n. You calculate this xn transpose xnw minus yn. And if you really want to, I want to again emphasize this, I can put this behind xn transpose, because although we have vectors here, but this is actually as a scalar, right? Because the first part is the dot product between xn and w, that's a scalar, and yn is a scalar. So in that case, we don't have to be worried about the order of these multiplications, right? So this is actually just a scalar, or in this case, a constant, which we can bring here. Once we calculate this, we subtract this from wk, and this gives us the new solution. And this is very helpful because now, every time we want to update these model parameters, we are avoiding matrix inversion, and we are only looking at one data point at a time. And this also takes us to the next important thing that we need to know when we talk about gradient descent and stochastic gradient descent, and is the concept of epoch. So think about it this way. If you have n data points or n balls, we can pick the first one, then the second one, then the third one, then the last one. So if you want to go one pass over the entire data, in this case, we have to do n updates, where n is this uppercase n, the number of samples. So in that case, one epoch means one pass over the data. But the nice thing is that we really don't have to just use one sample at a time. We can use two samples at a time. And it is very similar to what we have here, except now we are looking at two rows of the matrix X. Or you can have each mini batch of size 4. Usually it's common to use mini batches that are even numbers, 4, 8, 16, etc. And therefore, if we have a batch size of B, where B is the size of the batch, then the number of times that we have to update the model for one epoch is n over B, assuming that n over B is an integer. And in the extreme case where the batch size B is equal to 1, this means that one epoch means that n updates that we have to do using this formula. Something also I would like to add is that when we talk about stochastic gradient descent, we usually don't want to pick these data points sequentially or one by one from the beginning of the list. We want to do this randomly. So meaning that you randomly pick one of these n data points, and then you randomly pick another data point. And once you do this n times, then that's one epoch of one pass over data. And if you do this randomly, obviously some data points there might be repeated more than once, and there might be some that you have never observed, but that is okay. So usually it is more common when you do these types of sampling to do sampling with replacement, meaning that you pick a data point and then you put it back. And so this means that that data point in that epoch can be selected more than once. But obviously there are different versions, and you can have your own version that you do sampling without replacement. And that's the main idea behind the stochastic gradient descent, or SGD, that we have here. So the reason that this works very well, if you want to dive deeper a little bit into the theory, is that the loss functions that we have in machine learning, because they are basically empirical risk functions, and the empirical risk function is the average loss on the training data. So this means that this loss function can be written technically as 1 over n, the sum over n from 1 to uppercase n of the individual loss functions. And the gradient, because it's a linear operator, can be written as the average of the individual gradients. And now if you want to approximate this sample, this average, you can use a smaller sample size, meaning that now instead of working with the entire data, you can work with a mini batch of size B. And here we are using this, index T here too, if you want to use different batch sizes. But in general, we work with batch sizes of identical sizes, and therefore we can approximate this gradient on the entire function. And something that, again, going a little bit more into the theory here, that this is an unbiased estimator. And to show this, it's very straightforward. So let's say that you're working with a case that you select one sample at a time. So each mini batch only contains one data point, and define a random variable u, which is a discrete random variable. And it's also a uniform discrete variable, meaning that you have n data points or n different values, and the probability for each one is 1 over the total number of data points. And now if you find the expected value of the gradient calculated for data point with this index u, you can write this as the summation of the probabilities times the actual values. And since all these probabilities are 1 over n, so this will be out of the summation here, and you get 1 over n, the summation of the gradients calculated for all individual data points, and that's exactly the gradient that we wanted to approximate. So therefore, this approach where you randomly sample data points with replacement, so that's why that with replacement part is important, to make sure that every time you pick a sample, you can assume that you have this random variable that has the discrete uniform distribution. And therefore, the expected value would be exactly this gradient of the loss function calculated using the entire data set. And later here, we talk about the formula that we get if you only work with mini batches of size 1. And again, it is very important to understand the meaning of epoch here. So one epoch is one pass over the entire training data set. And so if you have n data points and the batch size is b, so in one epoch, we update our model n over b times. And we assume that n over b is an integer here. So now in order to implement this stochastic gradient descent, let's say that we have 50 epochs. Something else also to consider is that the learning rate or the step size shouldn't be just fixed across all updates. You can, for example, use something known as learning schedule, which is this function t0 over t plus t1. So this means that as you have more iterations, this function will give you a smaller learning rates. And this is a very common practice to make sure that as you do more and more updates, you are gradually decreasing a learning rate or a step size. So hopefully you get closer to your optimal solution and you don't have problems with oscillating around that optimal solution. And similar to before, we always need an initial solution. And then for each epoch, now we have to repeat this process n times, right? Because now each epoch, we have to go through the entire data. We assume that the batch size is 1, so we have to repeat this n times. And we have to select a sample using the discrete uniform distribution. And that's something we can do using this np.random.randint. We select the corresponding row and column of y. Or sorry, what I meant was we select the corresponding row of x and y. So we have to select the row of x index at this random underscore index. And remember, the way that slicing notation works in Python and NumPy, the starting index is inclusive, the stopping one is exclusive. So this means that you're only selecting the row that is at this location random index. And similarly for y, we want to select the corresponding row, and then we find the gradients, which is 2xi transpose xi w minus yi. And then we find the learning schedule. So because in this case, we want to make sure that we are not using a fixed learning rate. So we give the iteration number to this function. And the way that this works is that at each time when we are doing updates, we have passed this epoch number of times. And in each epoch, we have n data points. So we have epoch times n plus I. So when epoch is equal to 0, like when we just start, we are going to have this I here, which goes from 0 to n minus 1. And then when you go to the second epoch, which is the one with epoch equals 1, then you already have passed n times, and now you have to add I to that epoch times n. And the next step is to find eta, which is the newest step size, times gradients, and subtract that from w, and this gives us the new solution. So once we do this, now we can run this for 50 epochs and just visualize the solution for the final value of w that we have here, right? So we know that the way that we can find the output value is simply finding x times w, and this is a w after being optimized. If we run this, you can see that in this case, we can find a really good solution. So obviously, we're going to talk about this. You can use different metrics to measure how good a fit this line is. But visually inspecting this, you can see that this is a really good solution. And the other advantage here is the fact that the learning rate is not constant or fixed. So you can see that the only thing that we really need to define here is this T0 and T1, which can be used to show how fast this learning rate should decrease. And therefore, we are not directly defining what the learning rate should be, right? So in this case, it becomes less sensitive to the choices of T0 and T1 because the learning rate will eventually get smaller and smaller. And so even if for some reason we start from a value that is too large, then there is there is a system here to make sure that the learning rate gets smaller as we progress. The final thing that we really need to talk about gradient descent and stochastic gradient descent, which is very popular and something that can be used to further improve the performance gradient descent, is the idea of momentum. So what is momentum? Momentum is an extension to gradient descent that builds on the idea of inertia in a search direction. So in some sense, you can think of momentum as a ball rolling down a hill, which gains momentum with each step. And the idea is that we want to have this velocity so that if for some reason this ball gets to a point that is almost flat, has enough momentum to be able to overcome that local minima. So that's why momentum is very helpful for escaping local minimas, and also can help really with faster convergence, as it can really smooth out a lot of variations in the gradient direction. Because as we just discussed, especially in stochastic gradient descent, we are looking at only a small mini batch to find the direction of a steepest descent and then go to the opposite side. So therefore, using this momentum is very helpful. So how does this work? It is a very simple idea. So the update formula is very much like before. So you have your current solution minus eta times something that has the gradient information, and this gives you the new solution. But this new thing right now is what we call as velocity. And the way that this gets updated, it has a memory about the past values of this v variable plus the gradient at that current solution. So if beta is equal to 0, you can see that your velocity is just the gradient at that point or at that time. And you can use the standard gradient descent formula, which is theta k minus eta times gradient calculated at the point theta. However, when beta is greater than 0, means that now you remember a little bit about the previous gradients that you calculated, right? And you keep this memory, and that's what gives you the inertia or the momentum to be able to go down the hill when we think about it that way, about gradient descent. Something also I would like to emphasize here, we are using theta, and before we use w, but the point here is that all of these are the variables that we are trying to optimize. So it is very common in machine learning, deep learning to use W, theta, and so on. So, it is exactly the same thing, but, it's good to work with different notations. So, you really remember the main idea behind these update formulas. So the idea is that you have a current solution minus learning rate times the gradient or the velocity if we have the momentum approach. And here we have the exact definition of each of these terms for your review. But let's look at how this works in a problem that we have here. So let me just run this cell first, and then I'm going to explain about how we created this. So let's say you have a function that you want to find the minimizer, which is somewhere around here, but this has multiple local minimas, right? So it's a difficult optimization problem, especially compared to the quadratic function that we had before, like the x squared. So in this case, you can see that if we is start from the same initial solution and don't use momentum. We are taking these steps down the hill, but it's going to get really, really slow because we are just looking at the gradient at each solution and we don't really build that inertia. However, if we use momentum, you can see that if you look at the trace that we have here, you can see that now we get faster and faster closer to the solution in the same number of iterations that we have. And the final solution with momentum is actually very close to the, the optimal value that we have for this minimizer of this function. So you can see that if we tune these parameters correctly, so obviously you have this velocity parameter beta that we just talked about. So that's very important here. The learning rate is important. So all these, what we call them as hyperparameters, because these are parameters that are defined by the user and not learned through our machine learning approach. And if we set them correctly or appropriately, I would say, then you can see that we can get really, really good solutions with the momentum, and also we can avoid local minimas and so on. So if you go back to the functions, just explain what this is. So this complex function that you saw is an x squared plus some sine function. So that's how we get those nice local minimas. To just make this a more complicated problem, finding the derivative, or aka the gradient here, is relatively simple. And then we have now gradient descent with momentum, where the only difference is that when we want to update this x or theta or whatever the optimization variable that we have, instead of just using gradient at that time, we use velocity, and velocity gets updated as momentum times velocity plus gradient. So that's the main difference. And you can see that here we have the learning rate, the momentum, and also the number of iterations. So, obviously something that is really important here is this momentum. If it's too large, that can be a problem because this ball that goes down the hill can go too fast and pass the optimal solution. Or if it's too small, then probably you're not going to see a huge impact. So that's something, again, some of these hyperparameters that we have to correctly or appropriately specify. The final topic that we have for this video is regularization. So we talk about minimizing the differences between true and predicted values, which is exactly what we have here. And I'm not using any constants here, but if you want, you can use 1 over 2, 1 over n, and so on. But we know that that does not really change the problem very much because, the only difference is that you have to multiply the gradient by some constant. However, many cases, just minimizing the difference between true and predicted values is not enough. And we want to add more constraints on the problem in terms of the solution that we find. Because in many cases, for example, a simple solution is better than a more complex solution. And in this case, what we can do is to modify the loss function that we use. So before we had this L of W, now let's say we add this lambda, and this lambda is a hyperparameter again. So meaning that's something that you have to decide the strength of the regularization. And the way that this works, you add lambda times a function of W. In this case, this function C of W is a function that should measure the complexity of this solution W. And then the goal is to minimize the sum of these two terms, right? So there's a trade-off between how much we want to have a solution or W that is close as possible to Y when we multiply X and W, plus also we have this extra term that we want to make sure that this complexity is not too large either. And the choice of regularization is very important as well. And there are a couple of things that we can use. One of them that leads to L2 regularization is to use the L2 norm square of this vector W. And what this really does in simple terms, wants to make sure that we don't have any parameters or coefficients that are too large, right? So if you have a linear regression model, you don't want to have some coefficients that they get multiplied by these input features to be too large, because then small or minor changes in those inputs can cause huge differences in terms of the prediction. And that's in many cases not ideal. But there are also more advanced techniques, and one of them is L1 regularization, which is known as LASSO, least absolute shrinkage and selection operator. So this is a paper that was published early 2000s, and it was shown that we can actually use the L1 norm, which is the sum of the absolute values of a vector, as a regularizer. And in general, you can use the LP norm of a vector, which is the absolute value of each element of the vector raised to the power of p. We add all of them together, and then we have to raise this to the power of 1 over p, right? So when p equals 2, that's the 2 norm. And then when p equals 1, that's the L1 norm. But we can use this for any p greater than or equal to 1. But there are also other variants of these too. For example, like ElasticNet, which combines the L1 and L2 regularization. And the idea here is that, in many cases, it's hard to only pick one regularizer. So it may make sense to have a combination of regularizers. And in this case, we have this convex combination where rho is between 0 and 1, right? So if rho equals 1, then it's just L1 regularizer. And if rho equals to 0, it's just L2. And if some rho is somewhere between 0 and 1, that's what is known as the elastic net. So in other words, rho controls the balance between L1 and L2. So in order to briefly explain the differences between the two or how that can change the problem, let's look at the contourplots of these two regularization techniques. So what is a contourplot? Contourplot is a graphical technique that you can use for plotting three-dimensional surfaces. And since that's hard to do because we have only many cases two-dimensional spaces like your screen, we can use these by plotting lines or contours that connect points of equal value on that surface. So what we do here is that we create a two-dimensional grid from negative 1.5 to 1.5. Obviously, you can change these values as you want. And the L2 norm is sum of the squares. L1 is the absolute value of the sum of the absolute values. And we also have this rho, which is the balance between L1 and L2 terms. So you can use plt.contour for these contour plots, and you can tell this plt.contour to connect points of what values. So here, the points that they have value 1. That's what we want to connect for these three different types of regularizers or norms that we have. And also we have this C label to just add the label to make sure that each one is appropriately labeled by the type of the norm it is, like elastic norm, L1 norm, or L2 norm. And so if you run this cell, you can see that we get this very nice plot. So you can see that when we have L2 norm, all these data points that they're connected that they have value 1, they actually form a circle, right? And that's something we know. In a two-dimensional space, x squared plus y squared equals 1 corresponds to this circle. But then you can see the case that we have L1. And then since we have a convex combination of the two, so you can see that now the elastic net. So these are the contourplots, right? So meaning that, for example, if we care about what values for each of these curves take value 1, so this is how it looks like. But why is this important? So in order to understand the impact of regularization, you can think of the problem that we have for solving the loss function as a constraint problem, meaning that you usually have that negative log likelihood part, right? So that's this part that we have that corresponds to this y minus xw L2 norm squared that comes from the negative log likelihood function that we derived before. And then you had this extra term that we added to this loss function, but instead of adding it directly, we can think of this as a constraint problem, right? Where you have the norm of this vector, either the 1 norm or the 2 norm or a combination of 1 and 2 norms, less than or equal some value. And then in order to solve this problem, you have one surface that corresponds to this negative log likelihood function. So meaning that if we didn't, let's say, so think of this as like a ball that you have. So these, contours that we have inside, they correspond to the smaller values, and then the value of this function increases. And obviously, if we didn't have any constraint, this point would be the optimal solution. But now we want to find the optimal solution given these constraints, right? So we want to find where these things they intersect. And you can see that the solution can be really different because the point that this ball, I call it, hits this, L2 norm or L2 ball, you can see that it's very different than where it would hit this elastic net or the L1 norm, right? And since this L1 norm has these very like sharp edges here, so it is very likely the solution that we find is actually closer to zero. Overall, this is not a very complete proof of this, but we want to show you that the choice of regularization will impact the final solution that we find. And you can think of that regularized problem where we add the regularization term as this sort of like constrained optimization problem. And what really it is that we're trying to find the intersection between the surface that we have for this negative log likelihood, which is here the differences between y and xw, and where we have these L1 and L2 balls if we use these two types of regularization. There are other types of regularization too, but the mostly, we use L1, L2, and the elastic net, which is the complex combination of the two. So this is the last thing we do in this video. We are gonna import NumPy as NP. We're gonna work with one of the data sets that we have in scikit-learn, which is called the diabetes dataset. If you want, you can search scikit-learn, sklearn diabetes, and you can see what this dataset is about. And you can see that we can load this dataset by using datasets.load diabetes, and we want to have access to both inputs and outputs. So that's why we have to say return xy equals true. And what is really important here is the shape of these data metrics that we have. So you can see that given the notation that we have, in this case, we have 442 samples, and then we have 10 columns or features. And if you want to know what these values of features are, you can actually look at this NumPy array. If you want to look at the first sample, we can just put 0. So you can see that this is the input features we have for each patient that we have in this database. And then we can also look at the corresponding Y value. So that's diabetes Y. And you can see that that's also a real valued number. So as an exercise, I would definitely encourage you to look at this load diabetes and scikit-learn to get a little bit more information. But this is what this data set looks like in terms of just the number of samples, the number of features, and so on. And something that also we want to do here, since the goal right now is to be able to visualize models, and we can only do this if we have only one input feature, is to look at only one of these features that we have. So we are looking at the one with index 2, which is actually the third feature that we have since indexing starts from 0. And you can see that in this case, we have 442 samples, and we have only one column or one feature. So in general, we want to use all the features, but right now we want to just see what happens if you have one feature. And while I'm using np.new access, so I can remove these if I want to, but you can see that there is a problem here that, so I have to run this cell again, and I'll show you the problem. So the problem is that if I just use 2 here, and I don't use that np.new access, so I have these 442 samples with one column, but by default, NumPy will treat this as a one-dimensional array because we have one sort of like number here, comma, nothing. So that means that there is no second dimension or axis. And by default, when you want to pass these to many machine learning algorithms, such as scikit-learn's implementation of linear regression, they want a two-dimensional array, meaning that even though we only have one column, we want to make sure that that one extra column that we have is actually considered as a 2D array. So that's why we use this np.new access. And in that case, so I have to run this every time because I'm using the same name. So I have to make sure that I'm not using the wrong data metrics. So you can see that in this case, now the size is 442 by 1, which means that we have 442 rows and one column, and this is indeed a 2D array. And you can take this also using ndim. So if I use diabetes.x.ndim, so you can see that now this has 2 dimensions, or the rank of this is 2. Whereas if I remove this and run everything from beginning, so you can see that in this case, you only have 1 dimension. And that's a problem later on. So that's something we want to make sure we don't run into that problem. So I'm going to run this cell, look at what we have in diabetes data set. Now we have one column, and this is a 2D array. You can see here the number of dimensions 2. And here you can see that if you want to use a stochastic gradient descent for linear regression, this is actually already part of scikit-learn. So scikit-learn has a module called linear model. And inside that, we have SGD regressor. So you can click on this, get more information about all the inputs that you have. And as you can see, this is used for minimizing a regularized empirical loss with SGD. So all the things that we covered today. But the really important thing is that that's how exactly the implementation is in terms of constants and the way that they set up this. So we have this difference between y and xw. We have 1/2 number of data points. And then alpha is the strength of regularization, and rho is what changes the balance between the L1 and L2. So if rho equals 1, then that's just L1 regularization. If rho equals 0, that's just L2. And anything in between is a combination of the two, which is known as the elastic net. Finally, now that we have the x and y values, that's part of the data set. Now we can use, for example, I said the same value of alpha for our regularization strength. But what we're going to use is we're going to use this elastic net, but with 3 different L1 ratios. The first one is 1, and as we just discussed this, if that's 1, this is equivalent to the L1 regularization. When L1 ratio is 0, that's equivalent to the L2 regularization. That's why we use these names. And then we have the L1, L2, or the elastic net, and we use this mixing ratio of 0.5. And this max underscore iter is the number of epochs that we have. So let's define this cell. And so the next thing that now we're going to do, so because we're also doing the fitting here, so this means that the models are trained, we just need to do predictions. If you remember, in this case, we always have to create new data points for our testing or validation. So that's where here we're looking at the minimum and maximum values and create technically space points. We can only really do here 2 points, but again, it doesn't matter. You can use always more data points, especially if you know that you want to work also on some nonlinear models later on. And we're going to plot these 3 models that we have by looking at the predictions. So we give the same inputs, but now we have different models that are predicting. We're using 3 different colors, 3 different labels, L1, L2, the elastic net or the combination. And if you run this cell, you can see that the solutions that we find here are very different, right? So this is the solution when we have L1. This is the solution when we have L2. And then when we use elastic net, this red dotted line or dashed line. And you can see that in this case, it's really hard to solve this problem in the sense that it really depends on what we prefer, because there's really no right or wrong solution. In many cases, these extreme values that we have here, there might be outliers or noisy data. So maybe the reason that this orange line is closer to them is because of these outliers that we have, and actually we would like to reduce the impact of these on the solution. So this means that in that case, L2 or L1 plus L2, they can be better solutions, but it really depends on some usually like, side information or extra information about the problem. And it shows you that many real world problems are complex, even in this 1D problem to solve. I hope you found this video helpful, and thanks for watching.